Hello, good day, and welcome to the Advanced Material Forum. My name is Rob Demand, and I will guide you to a presentation on making and breaking the electrical power distribution. Due to the current corona situation, we are recording this presentation from our home office, so the setup looks a bit different, but we will manage. If during my presentation you have any questions, you can ask them in the online chat and you will be replied to as quickly as possible. Like mentioned, my name is Rob Demand. I'm application development engineer at DSM Engineering Plastics. I'm based in Geleen, Netherlands, and I have 25 years of experience in application development projects with E&E customers, of which the last 15 years at DSM Engineering Materials. In this presentation, I will briefly touch upon the applications in electrical power distribution. I will discuss a polyamide 6 solution for electrical housings, various switching mechanism solutions, stenil polyamide 4,6 for high performance electrical housing, and I will discuss arc quenching technology with stenil CR310. In the current society, the energy consumption is constantly rising. More and more energy is consumed, and this puts high strains on the electrical power distribution devices and on the grid. So there is a clear need for higher performance materials. Also, due to this higher energy consumption, there is an increased emission of CO2. Now, if we, with our engineering plastics materials, by introducing renewable materials can help in reducing this CO2 emission, that would be great. Electrical power distribution, low voltage power distribution, we divide into three main segments. And on top, electrical installation. These are mainly your wall switches and sockets. This market is mainly dominated by styrenics, although in the internals you also see some polyamide 6, 6,6 and PPS. But I will not go further into detail into this segment. Bottom left is low voltage switchgear. These are your typical MCBs, miniature circuit breakers with residual current devices you see in your electrical panel boards at home. And the bottom right hand side is the control gear segment where contactors, motor starters, thermal relays are situated. This is more the industrial protection and control of electrical devices. How does this look in a diagram like? You have your power distribution, and on the left hand side your industrial distribution, which starts at the high end with an air circuit breaker capable of cutting high currents, and then it goes down in current to a molded case circuit breaker, and even further down to final distribution MCB, RCD, contactor, motor starter, so the typical protection and control equipment for electrical devices. So from the top to the bottom, the current to break is reducing. On the right hand side, residential distribution, also in some cases an air circuit breaker, for instance to protect the complete apartment block. And then quickly to the MCB, RCD and RCBO, your typical devices in your electrical panel board at home, mainly for protection of people, but also electrical devices, of course. For the residential distribution, the MCBs that are used have different ratings, and depending on the rating, every time a different material is used. So various material solutions are used in this segment, from 25% mineral filled, 20% glass filled, 30% glass filled. And this is quite a hassle from a technical and from a commercial point of view. So in the market, there was a request for a one-size-fits-all cost-optimized solution. Now, based on this market request, we developed COKGV5, and if you can see on the left bottom, COKGV5 with the mechanical profile, tensile strength and tensile modulus fits well between the KGV4, the 20% glass filled, and the 30% glass filled solution we are currently supplying to the market. And this mechanical profile is confirmed by our customers to fit the needs for a one-size-fits-all solution. Of course, this material also needs to have the other standard requirements for an MCB housing, like halogen-free flame retardant with the proper glow wire performance, CTI 600 volts, and last but not least, an HDTA of 170 degrees. So this material, Archelon polyamide 6, COKGV5, is designed for standardized, cost-optimized mass production. If you look at the MCB internals, there are various functionalities which all have their typical requirements. On the left-hand side, you see that for the enclosure, of course, you need a certain electrical performance, a certain flammability performance, and of course, a certain mechanical performance. The bobbin support. The bobbin is the system that initiates the short circuit operation. One needs a high tensile strength and high impact performance. Since electrical devices operate by creating an arc for cutting the current, this arc quenching is very important. So in the flange, materials need to be used with a good arc cutting and quenching behavior, and of course low soot formation. Since the mechanism is a complex electromechanical system, this needs to operate flawlessly under all circumstances at the same forces. Therefore, in the switching mechanism, one requires materials with low creep, low friction, and high dimensional stability. If you look at the enclosure materials, of course, on the left, we already mentioned Archelon polyamide 6, COKGV5 solution. But if the ratings of the circuit breaker increase and there's a higher thermal load on the housing, polyamide 6 is no longer sufficient and one needs to switch to polyamide 6,6. One of our solutions for this is Archelon SGKGS5. This is a polyamide 6,6, 25% halogen-free flame retardant. Even at higher ratings, we position Stenil HFX 63S, halogen-free flame retardant 35% polyamide 4,6, and for the highest ratings, we position a PPA, a 4T11. For the bobbin support, because it requires high thermomechanical performance and high impact, we position Stenil TE200F6. For the flange, normally unfilled polyamide 6,6 is used, and for increased arc quenching performance, Stenil CR310. Stenil CR310 is specially developed for its arc quenching properties, and I will go into more detail into this later in my presentation. For the switching mechanisms, we position dimensionally stable materials, Zytron PPS. It's a Teflon modified grade to ensure proper wear and friction, but also Arnite PET 35% glass fiber filled. In electrical power distribution, due to the increase in energy consumption and in a more different setup created by smart grid, electrical cars, connected home, solar panels, there is an increased complexity in the electrical devices. So the devices need to handle more power, they need to be smaller, they are more integrated with electronics. Therefore, there's a clear need for high performance plastics. The properties that are then important to ensure proper operation and to achieve all the functionalities are, for instance, higher flow, increased ductility, high temperature resistance, also high thermomechanics, and halogen-free flame retardant. And of course, because we all want to work towards a more circular world, the usage of sustainable materials is a big plus. Now, if we look at all the requirements that are there for this new high-performance plastics, we see that Stenil can be positioned in this field very well. Stenil is a polyamide 4,6, already on the market for 30 years, has earned its position in various automotive, electronics and electrical applications. In the past, mainly non-flame retardant and halogen containing flame retardant, but with the drive towards more halogen-free, in 2008, Stenil cotton rose was developed. Cotton Rose is a flame retardant developed by DSM, and next to its flame retardant properties, it also shows excellent arc quenching properties. Further developments have led to Stenil HFX Generation 1 and the currently positioned Stenil HFX Generation 2, which we position for electrical in the electrical power distribution segment. Recently, also Stenil has been made partially bio-based, so it can contribute to the circular economy. The bio part of Stenil is based on tall oil, and this is produced from a waste product from the paper industry. This bio-linked Stenil is pretty well in line with the strategy of DSM, where by 2030 we want to have a full portfolio either bio or recycle based. If we take a closer look at Stenil HFX, the material we position for high performance electrical housings, in this case Stenil HFX 63S, you see that the mechanical profile perfectly matches the needs of this market. The material is halogen-free flame retardant, shows proper flame retardancy, high CTI, and excellent short and long-term thermomechanical behavior. One of the biggest advantages of using this material is that it shows no corrosion during processing. Stenil is an aliphatic polyamide, polyamide 4,6, and has a similar glass transition temperature than other polyamides in the market. So as soon as the material goes above its glass transition temperature, the mechanical properties will drop significantly. But with Stenil polyamide 4,6, due to its high crystallinity, as you can see in the yellow curve, above Tg, the mechanics are highest compared to all the other polyamides and PPS in the graph. So above Tg, Stenil shows the highest mechanical properties, which are of course beneficial for the dimensional stability of the electrical device. For electrical devices, like I already mentioned, the housing in general is either polyamide 6, and if it doesn't work thermomechanically anymore, the switch is made to polyamide 6,6 and then to a PPA type material. Now, the jump from polyamide 6,6 to a PPA is quite big, both in performance as in price. And also PPAs exhibit corrosion during processing, which puts extra problems in the process stability of the equipment and the parts produced. In this gap, there is a different material positioned. It's called a high temperature polyamide. Now, if you look at the property profile of this material, which has been approved in various applications, one sees the typical mechanical profile with an HDTA of 250 and a melting temperature of 280. So pretty good thermomechanics. Now, this material functions well in the gap between polyamide 6,6 and PPAs. Now, if you look at the property profile of Stenil HFX 63S, you see that our material matches this mechanical performance and even outperforms this material thermomechanically. So if you look at the HDTA, it's 285 instead of 250, and a melting temperature of 295 instead of 280. So this makes the application window of Stenil HFX 63S even bigger than the high temperature polyamide. Stenil is of course not new in the electrical power distribution market. It has been used already for many years in electrical applications, like is shown here, like the base of an MCCB, the tripping unit, contact holder, and the arc chamber parts. This was mainly done with halogen containing flame retardant Stenil grades, but it shows that the basic property profile of glass-filled Stenil perfectly fits into the electrical power distribution devices. Now, electrical protection devices cut the current by creating an arc, and this arc needs to be quenched to stop the current from flowing. The longer the arc stays in existence, the longer there is a hazard for severe damage to people and the equipment. Now, this arc is normally quenched in an arc quenching chamber. Materials used in this field are BMCs, thermosets, or blends of POM or polyamide for gas generation. This gas then dilutes the arc and pushes it into the arc quenching chamber. We have developed the materials, stenil Cr310, which shows much faster arc extinguishing performance due to excessive gas generation. Also, does this stenil Cr310 result in a higher isolation resistance after short circuit? The material generates a limited amount of soot, and as you know, soot is electrically conductive. So if there is a lot of soot in the breaker, it can cause electrical failure and even restrike and flowing of current again, and inducing all kinds of issues. So the less soot there is formed inside the breaker, the higher the isolation resistance, the higher the safety of the device. Now, what have we done to prove that stenil Cr310 works perfectly in these type of applications? We have taken a single pole MCCB, 100 amp, 25 kiloamp short circuit performance, and replaced on the bottom right the arc quenching chamber, which was made out of thermoset. We replaced it by stenil Cr310 and did various short circuit tests. For the rest, we did not change anything in the device. Here you see the graphs of this short circuit performance. In the dark blue line, you see the voltage curve of the stenil Cr310, and in the light blue curve, you see the voltage curve of the thermoset. In arc quenching, it is important that the voltage is driven up as high as possible, because the higher the voltage, the more easier it will be to cut the arc. As you can see, the dark blue line goes much higher than the light blue line. So there's a much better voltage rise, which will make the arc cutting much easier. For the current, one sees the dark red line is the current curve of stenil Cr310, and the surface below the curve is the dissipated energy. For the light red curve is the curve for the thermoset material, so the initial material used in the arc shoot. And there you see that the surface below the curve is much bigger. So there will be more energy dissipated. So there is more thermal load on the housing. Also, this curve shows that there is no restrike. Once the current is zero, it will stay zero. In other arc quenching materials, when there is a lot of soot formation, this soot formation can cause restrike and reinstating of the current. How does this look into the numbers? To be sure that this performance is not only once, but works multiple times in a row. We have done 3 consecutive short circuit operations on the same device with stenil Cr310. That's the top end of the table, and we compared it to the thermoset performance on the bottom end of the table. So if you look at the second column, arc voltage, you will see that the arc voltage of stenil Cr310 is much higher, 345, than the 305 with the thermoset material. Also on the complete right-hand column, in the last column, you see I to the power of 2 times T, so the dissipated energy. You see that with 533, this is much lower than the one with the thermoset of 897. So also in the second and third operation, you see that the arc voltage is still higher and the dissipated energy is still lower. So by introducing stenil Cr310 for high performance arc chamber, the devices get better electrical endurance, so they can work much longer and much more operations. There's a lower thermal load on the housing, so this opens up possibilities for lower end engineering thermoplastics. And of course, due to the two above phenomena, it is an increased, that shows increased safety. So stenil CR310 is the ideal solution for a high performance arc quenching chamber. DSM Engineering Materials has a large portfolio of engineering thermoplastics, as you can see in this graph. It goes all the way from PBT, polyamide 6, 66, PET, PPS, sustainable EcoPax, polyamide 410, already discussed polyamide 46, and our PPA 40, PA40. Now, based on all these base polymers, we have developed a complete halogen-free flame retardant portfolio to match the needs in the electrical segment. In this diagram on the left-hand side, you see the thermomechanical performance of the material, and on the bottom, on the x-axis, you see the flammability. So from bottom left to top right, you see an increase in thermomechanical performance and an increase in flammability. All these materials are halogen-free flame retardant. As you can see in the different grade codings already discussed, Archenon COKGV5, a polyamide 6 one-size-fits-all solution. Stenil CR310, our arc quenching material. Stenil HFX63S, our stenil halogen-free flame retardant we position for high-performance housings. But also all the other materials like Citron for internals, polyamide 66 for intermediate solutions. So we offer a complete portfolio for usage in electrical power distribution. This is my last slide. I hope that you learned something from this presentation. If you have any questions, you can put them into the chat. Thank you for your attention.